Hello, this is a further maths FP1 video on something we call the Agrand diagram. We see recapping complex numbers and complex conjugates in that, and then we'll be going on something called the argument. Now, that's not something you would have with your friend. This is something completely different, unless you were arguing about maths, perhaps. But anyway, let's get on to some of this real stuff. So you will have obviously come across something like this, where you have a graph of y and x. So you have a y-axis and an x-axis. But that was just a build-up. So you've got your y coordinate. If your y was 3 and x was 4, you draw up to 3 and 4, depending on your what graph you were looking at. But an Agrand diagram uses that kind of concept, but instead of having x and y, on the x-axis we have something called the real numbers, and on the y-axis we have something called the imaginary numbers. Now, we said the imaginary numbers is just something that is root minus 1, we call that I, so therefore 2i, it'd be 2 root minus 1, etc. We kind of describe that. Now, a real number, again, is just any number that you can think of that's logical, that works. So 3,699 could be one. Just to name one. Okay, so here comes a question. When we have an equation like this, obviously this particular one on this graph is y equals x. But if we had something like y equals 2x plus 3, then we'd go, okay, well, each y coordinate is 2x plus 3. It's kind of a little bit different when you are drawing an Agrand diagram. So say we draw complex numbers. If we were to draw a complex number on this diagram, and that's because it's just a number, so it's not a graph as such. So say Z1 is equal to 3 take 2i. Now, a key thing from the Agrand diagram is you always start from the centre, okay? And then you draw a line out to wherever this particular point may be. Now, you might have something like 2i squared, etc. But in that case, then you would just, because squared is obviously root 1 times minus. If it was squared, then you could simplify this, and Z1 could equal just a number. And it'd just be sort of a straight line sort of thing. But if it was something like this, so how would you draw that? Well, as I said, you start from the centre and you go to the point. You can almost think of it 3 minus 2. So minus 2 is in the imaginary sense, so it's 2 down and 3 to the right. So you just sort of put it's 2i over there somewhere, and you draw a line to it. That's essentially what an Agrand diagram is. So you could come up with anything such as this. You could even have 2i take 3 and be the other way, etc. But you just draw something from the centre to a given point. But how does this help us? I mean, it's very good, but surely in further maths we're going to take this further. Well, we are. Now, I've just mentioned at the beginning something called an argument. Now, an argument is an angle. A key thing. So I like to, the way I see this is, I mean, it helps if you've done C2, but I'm not saying you would have done, or whatever. It depends where you are. But what I'm going to refer to now is something called the cast diagram. Now, I will give you a quick bit of an explanation if you've never heard of it before. But obviously I can't switch myself off and shut myself up and mute myself to different people. I've absolutely no idea what they're studying, but I'd like to think it's something to do with further maths at least. Watching this video anyway. Anyway, so I'm sure I was going on about something quite important, but whatever. You get the joy of not listening to me waffle on about that. So anyway, we're talking about arguments now. Arguments, as I said, are angles, and I said I was going to relate to the cast diagram. Now, don't worry, I'm not going to start drawing. It's nothing to do with trigonometry, even though the cast diagram kind of is. When we look at a cast diagram and we try and find an angle, we generally are given a range, and we do something like that. And we say, oh, all that angle there is theta 1, and you measure theta 1, and you can get different angles within certain ranges. So this is kind of different. This is kind of the same thing, because we're still measuring angles, but you can almost think of it as there's a constant, because we're not dealing with anything else then this kind of number on an Agrand diagram, at the moment we're concerned with, we'll always have the same range. It's just like dealing with the same kind of trigonometric problem, if you can think of it like that. As I say, it's nothing to do with trigonometry, but helps me, so stuff the rest of you. Great. Anyway, so we always have a constant range, if you think of it. It's between minus 180 and 0, or 0 and 180. Okay, it's never outside that range, and it won't ever be on it. But you know, you could put them little dashes there if you want to, but it'd never be on it, because otherwise it wouldn't be a complex number. I mean, you could write 0i, but then what's the point of putting 0i? Just write 3 if I was 0 on there. Okay, so how does it apply to something like this? So we've drawn this here, which is Z1. Okay, but if we wanted to find the argument of this, then we'd draw as we want it in this range, but we want the angle. It's the same way you would draw it. Now, obviously, we can't go this way because obviously the 180 is here, so we can't really go past 180, so we can't do it that way. So therefore, the only way we can do it is going back, sort of in a negative sense, really. Okay, so all we're doing is going in a negative sense. So whatever this angle is here, that will determine what the argument is, because the argument is the angle. Now, you know, in some cases where you might have something over here, then you would have to take this away from 180 or whatever. But because we're in a negative sense and it fits in this perfectly, we don't have to do anything else. However, to work out this angle, we're going to need, obviously that's the angle a bit big, it's more like that one. We're going to need the height and we're going to need the length. Now, this doesn't tell us anything. This is just almost a vector, so to speak. So you do it in the same way you would find out the length of a vector. Or whatever way you want to think of it, because you think of it the same way. So what this says is we've gone 3 to the right, so therefore the bottom bit is 3, and 2 down, so therefore the length is 2. And we just use Pythagoras' theorem, which says the square root of AB squared equals C, so this is C squared. So therefore it's 3 squared plus 2 squared, which is obviously 9 plus 4, which is root 13, which is the length of the complex number on the Agrand diagram. But we want this little theta there. So you could go from whichever way you want it to. It's up to you, but it's just now a right angle triangle, and you'd use standard trigonometric functions. I'm not going to dumb it down too much because I don't want to insult you. But hopefully you understand that. I mean, you know, if you don't get it, and I'm just assuming you do, not because I'm lazy at all, no, definitely not the reason, then please do let me know and I'll show you something like that. But just want to get the main maths bit out of the way, so, you know, if I do upload some questions, well, I might do in a minute, depends how we go on with this video, you know, you're not going to be bored to death quite just yet. Right, so hopefully you understand that. That's just an argument. Finding an argument, finding the angle. There's many variations on that. As I said, I will do quite a few in a minute, but I just want to get the main maths theory out of the way. Okay, so as I said, hopefully you get that. Now, when we were looking at complex numbers, I'm just going to look this out so I can start again. When we were looking at complex numbers, we looked at something called the complex conjugate, and it's a very fancy word for just saying we change a sign in front of the imaginary number. So if we go back to our good old friend that Z1, which was 3 take 2i, therefore the complex conjugate of that, Z1, what we call Z1 star, is 3 plus 2i, because all we've done is changed the number, the sign in front of the imaginary number. Okay, and obviously these two together we call the complex conjugate pair. Alright? But how do we represent these two on the diagram? I mean, say for this, because we would like to relate to that famous thing what was y equals mx plus c. How do these two show? Obviously, we'd have to draw this on an Agrand diagram, because that's why you have them, so we can draw complex numbers. So, go back to our real for now, just put r real and I am imaginary. So, this 3 take 2i, the first one I'm going to draw. Now, we drew that before, and it was something like this. Okay. But this Z1, a key thing, because this is plus 2i, yes, if we didn't know this, let's just draw this Z1 star, then it'd be something like this, because it'd be 3 up, 3 to the right and 2 up, yeah? Whereas this is 3 to the right and 2 down. So you could try this for anything like this, where we have the complex number, then you would always end up with the reflection in the x-axis. So if this was 3 minus 3 plus 2i, or 2i take 3, then it would go like this. And if we did the complex conjugate of that, then it'd be like that. So we've got an x there now. Okay? So it's almost thinking, if you can almost imagine, say if the complex number had just an equation y equals f of x. Now, obviously it wouldn't, but because the axes wouldn't be relevant and you couldn't do that, and we don't have an x in there for a start, and we don't have a y, then you can imagine, if you imagine the complex number as that, and you can imagine the complex conjugate is reflecting the x-axis, which is minus f of x. Okay, something like that. So it depends how you want to think of it, but I mean, if you're doing it first year, I'm assuming you've been doing C1, so that's quite relatable, I think. Alright, that's just, I mean, you can totally ignore that, as I said, and just do your own way of whatever you want to do. But you know, that's totally up to you. Okay, so that's the main maths of this video out of the way. What I'm just going to do now is going to pick some quick questions that we can have a go at, and we'll see you when I pick them. Right, so we've got some questions there that I've kind of written on the board. So obviously we're going to be drawing the complex number on the Agrand Diagran sketches I've done there, and we'll be finding the argument or the angle. Now, if you want to have pause video and have a go, I'll just read them out for you before you do. So this is z equals 2 plus 7i. This is z equals minus 5 plus 2i. This one, z equals minus 1 plus I. Z equals 3 take 7i. And finally, z equals minus 4 take I. So if you want to pause the video and have a go at this point, you're obviously more than welcome to. And obviously I'll be going through them anyway, so if you want to be quite lazy and you know, whatever, it's totally up to you. So you can just give you a second to pause the video now, and I'll shut up so you can tell when I've resumed. Right, okay, well, hopefully you've had a go at them. Now, the first one I'm going to do is the bottom left. So we do what we always do. So it's 2 to the right and 7 up. So we'll just draw a line doing such. Okay. So as long as it looks something like this. Okay. And then so you've got a height of 7 because that's in the imaginary sense. So you've got 7 there. It's gone across 2 in the real sense. So therefore you do the square root of 7 squared plus 2 squared, so it's 49 plus 4, which is obviously root 53. You can't do anything else with that, so that's all we do. And the little theta is there. Now we don't need to do anything else. We can just work out what theta is. So the way I write it is root 53 times cos theta equals 2, which is there. Rearrange that to get theta and cos inverse both sides, so theta equals cos inverse of 2 over root 53. And if you were to whack that into your calculator, you should get an answer of theta being equal to 1.3 radians. Remember, we're in radians. I'm doing all these in radians, by the way. Okay? So as I said, that's totally up to you. You could also do another way is doing, okay, we could do your tan theta, so you wouldn't need to work out what this 53 is, root 53, if you just wanted to go straight to find out the angle, but you didn't want to work out what the mod of z was, then you could just do the tan theta is equal to 7 over 2, so therefore theta is equal to the tan inverse of 3.5, or 7 over 2, and you should still get, if you use the radians, you should get 1.3 radians. Now, that doesn't, if you put that in your calculator, for those of you who've actually bothered to see if I'm right, or genuinely don't believe me, it comes out to be something like 1.2976 or something. But as long as you get, I round it up generally to two significant figures or one decimal place, so either one would be fine. Okay, so the next one I do is this one on the right. So it says z equals -5 plus 2i. So it's it's -5, so it's to the left by 5 and down 2, and it's from the origin, remember. Okay, so we're going to draw that. So it's -5 and then 2 up. So it goes something like that. Do the same thing we did over here, where we draw our little right angle triangle on this. You get a pen. So we've got a height of 2, it goes across 5, and if you could, as I said, you can always just continue to use the tan method for this. But I want to go the official way round. So it's the square root of 2 squared plus 5 squared, so it's square root of 25 plus 4, which is 29. So it's just the square root of 29. So therefore I'd write it out, so theta is there. However, we've got a bit of a problem here, and this is one of the ones that I like to point out. So I'm going to call this angle A, not theta, but A. Now, remember our range. We can work out what A is, and that's very good, but remember that isn't in the range, because we want the range to be between 0 and 180, or minus 180 and positive 180. Now, if we did that, that wouldn't tell us anything. That would just tell us the angle A. That's not going to tell us the argument. Because that's why it's important to think of it as though you're doing a cast diagram. Because you wouldn't start a cast diagram from there, would you? And you wouldn't start going backwards and forwards. You would mess it up. So that's why I like to keep your mind thinking about it as though it is a cast diagram, only really in that sense. Alright, otherwise you could just plonk this anywhere. It wouldn't have to be on this graph. You could just do it anywhere, so it'd be pointless using this graph. So that's why we use it. Okay, so anyway, do the same thing you would do here, but when you get the answer here, because this is essentially when we're looking at a cast diagram, that's pi, so it's pi take that. Or obviously it's plus or minus pi on either side, on this side, sorry, but, right, so, okay, so you're thinking about, okay, so it's root 29 times the cos of A equals 5. Rearrange that, so A is equal to the cos inverse of root of 5 over root 29. So therefore you get an angle for A. If you whack that into your calculator, as being 0.38 and etc. I'd leave that in your calculator as an answer, but remember we want the angle we actually want is starting from the real axis and it goes over there, so we want that angle, or this theta. So what we'd say is theta is equal to pi take little a, so therefore theta is equal to pi take this 0.38 etc. Whack that in your calculator, sort of whacking here. Hopefully your calculator doesn't break. You should get an answer of 2.76. Don't remember to say that's radians, I'll put a little C next to it to indicate it is. Okay, as I said, you can go from this way of using tan, but I just prefer to use it properly. Right, the next one we're going to do is z equals -4 take I. So really, that is probably going to be the hardest it's going to get. I mean, they might do it underneath this. I mean, obviously further maths gets a hell of a lot harder than this, but for this particular aspect of it we're looking at in terms of using Agrand diagrams for modulus, in this kind of context, obviously we add a bit more to this in the next video, but at the moment that is as hard as it kind of gets this video. And obviously have it underneath as well, which might be a little bit harder, but anyway, so -4 take I, so it's to the left by 4 and down by 1. Okay, so we have this here. So we're drawing the same thing. Sorry, I just prefer using green, so I know I am. It's going so smoothly this video as well, you know. I wasn't making a mess of it. Right, so draw our standard line. Okay, and then we draw our little things on the side to make it a right angle triangle again. Okay, and obviously we can't work out what this theta is, but the theta we end up working out is like the one we had over here, which is that one. But to be able to work out that, we need to first work out what this little angle is here. So call that A again. Alright, now using the information we've got, we look at the lengths of it. So it's got a height or a depth of 4, and it's 1 to the right. Now that's not proportional in terms of these other ones, obviously they would be a bit bigger, but I'm just obviously not doing it to scale. Do the standard thing, so you can either use tan formula, but I'm not going to keep doing that because I just prefer personally just using it as a normal kind of function really, so keep it constant. So what you do is it's equal to the square root of 4 squared plus 1 squared, so that's equal to the square root of 16 plus 1, which is obviously root 17. Now you can't simplify root 17 any further, so you can just leave it as that. And then therefore you would say root 17. Now you don't put is equal to minus 1 or whatever because you can't have a length that's minus 1, so this is why doing this way might be a little bit confusing. So root 17 times cos of little a is equal to 1, so therefore little a is equal to the cos inverse of 1 over root 17. Sorry, I'm going to move that bit out there. And then you get an answer for a. So in this particular context, A is 0.2449. But just as we did over here, that isn't the answer, so we have to do theta is equal to pi, take that answer, just upside down, but it makes absolutely no difference, to 449. Okay. Well, it doesn't make any difference in terms of we still count it, but obviously we have to turn this sign positive because we're going the other way round. So therefore this gets us an answer for theta as 2.9, so 2 decimal places. But obviously it's not just 2.9, it's minus 2.9 because we're going in a negative sense, remember. This next one, 2 equals 3 takes 7i. Well, do this in the way we've always started these questions. Draw the line first, so it's 3 to the right and 7 down, so it looks something like that. Now we don't have to do any of this pi business, we can just, it's just another way of doing what we originally did. Okay, so you draw your standard thing on there, you get a theta there, and then you work out how far it's gone along in each sense. So in the real sense it's gone to the right 3, and down 7, but you just call the lengths 3 and 7. I'm going to do it as we always have done, so it's 7 squared plus 3 squared, so it's it's 49, root 49 plus 9, so that's root 58. Can't do anything with that as we couldn't do anything with the other ones, so it's root 58 times cos of theta equals 3, theta equals the cos inverse of 3 over root 58. Okay, and then you should get an answer for theta equal to sorry, I was getting myself there. Didn't have it on the right page. Greek takes 7i. Sorry, if might have skipped something. Oh no, no. You should get an answer for theta of 1.16. Now that's negative, remember, so it's negative 1.16 because you're going in a negative sense. Finally, minus 1 plus I is kind of like this. It's pretty much the same method as this one that we've got over here. Obviously these answers are all correct, so you can check yours as you're going along. Okay, so it's 1 to the left and 1 up. So we have something like that. Then we draw our standard with the little bits on. So we have a line going down there. We want to work out this theta, but to work out that theta we call it little a. Sorry, and we want to know what little a is so we can work out what big theta is, which again is that thing. Okay, draw the what you've got. So it's 1 to the left and 1 up, and obviously that gives you a length of root 2. So therefore root 2 cos of little a times root 2 is equal to 1. Therefore a is equal to the cos inverse of 1 over root 2. Okay, so we get a value for a which is equal to sorry, I haven't wrote this answer down properly, so I just have to do that on my calculator. So you do the cos inverse of 1 over root 2, which I get an answer of pi on 2, pi on 4, sorry. 2, whatever. Let me convert my calculator to radians. Yeah, pi on 4. So you get an answer as pi on 4. You do theta is equal to pi, take pi on 4, or theta is pi, take little a, which gets you obviously 3 pi on 4. Okay, so they're the answers to the questions that we've just gone through. Hopefully it's been some use, not a complete and utter waste of your time. I only like to waste a little bit of your time. But anyway, hopefully that's been helpful. It's quite a nice topic, I think. There's definitely nothing untoward in that topic that you couldn't simply work out just from looking at that. Okay, so thanks for watching, and we'll see you in the next video.